I'm from Deakin University, and I'm going to chair the session today. So we're having 4 outstanding, well-known speakers, so I don't need to introduce any of them. We are having Professor Miryung Kim from UCLA, Professor Tim Menzies from North Carolina State University, Dr. Krysta Svore from Microsoft Research in Redmond, Washington, and Professor Myra Cohen from the Iowa State University. So we're going to have the session in 2 parts. In the first part, I invite the speakers to talk for 10 minutes about their research, and then we're going to have 15 minutes of panel discussion. So if you have questions on the first part, please keep the questions until the second part, and then you will have 15 minutes to ask your questions, and then the panel will discuss the questions. So the first speaker we have is Professor Miryung Kim talking about software engineering for big data and hardware heterogeneity. So over to you.
All right, thank you. Thank you. All right, my name is Miryung Kim. I'm a professor at UCLA. So traditionally, software engineering tools and development tools focus on analysis of software artifacts, mostly like programs and code written in Java and C++. Today, I want to discuss the new trends of software development in a data and compute-intensive domain. I hope I can motivate our software engineering community to pioneer a new wave of software engineering tools in this data and compute-intensive domain. So some of you may know that I studied research investigating code clones, automated refactoring, and mining software repository by really applying data analytics or AI techniques to the repository data in GitHub and Stack Overflow and many artifacts available. About 9 years ago, I spent my summer doing research, like investigating the role of an emerging data scientist at Microsoft Research, and this really changed my heart. So I moved on to this domain of data-intensive software development, and I started building like automated debugging and testing tools for big data analytics, mostly like these frameworks like Apache Spark that works on distributed data-intensive framework. And this experience taught me the importance of systems and runtime. And more importantly, later, I realized that all this research is actually enabled by like some of this advancement in hardware heterogeneity or hardware acceleration or advancement in computer architecture. So in the past 4 years, I sort of moved on to developer tools to incorporate hardware heterogeneity or lower the barrier of leveraging hardware heterogeneity. So right now, I'm really excited about this new opportunities of software engineering tools in this data and compute-intensive domain. So this is one slide that I hope you can take away. What is the current context and future context of software engineering? There are many challenges exist that make software engineering tools to be tractable in this data-intensive and compute-intensive domain. The scale of inputs is huge, large, like extremely large. There's a long invocation latency for invoking in program, but also compiling these hardware synthesis. Of course, debugging is hard. Injecting debuggability, visibility, and traceability into runtime incurs a performance overhead. And these systems are built on layers and layers of runtimes and systems and compilation framework. So today, I'm going to just talk about what is the current context. So let me first start with the context of software development tools for big data analytics. Broadly speaking, data-intensive compute framework, such as Apache Spark, Google's MapReduce, or Hadoop, or these type of domain. So let's consider developer side or workflow. You know, when you are thinking about AI, the first step is actually creating a data and ingesting data and getting features out of this. What is the current development lifecycle? Developer usually has a terabyte of data sitting somewhere in S3 or like storage bucket, which is collected from this telemetry or large data collection. Developer writes these applications using, let's say, Apache Spark or this Hadoop type of a framework. And these data analytics applications are usually tested locally on a sample data, maybe like 100 or 1 gigabytes of data sampled from these very large scale data. You execute on the cloud, then after that, hoping it will work. You submit a job, maybe go get a coffee. You come back and then see that, oh, maybe there was a runtime failure exception. At least you know that there is a crash. But a lot of times you get a result that looks suspicious to you. Oh, two-bedroom condo price in Kansas City is 20 million. That sounds kind of suspicious. Then they analyze the data or keep digging through it, update the application, resubmit the job. And in some sense, the debugging and testing in current big data analytics system is almost like a debugging in the dark ages. What is it like from a kind of system perspective? Users write these applications, let's say when you are working on Apache Spark, using these data flow operators such as a map and reduce, or relation operators such as a join and group by. And unlike SQL, people write arbitrary application, let's say 1,000 lines of code to parse or extract these features from semi-structured or unstructured data. Once you submit the job, these applications run a distributed computing framework that actually runs on multiple partitions of data in parallel. These frameworks are extremely complex because it has a highly optimized, distributed, lazy evaluated computation. And, these frameworks contain higher order functions, portion of a query optimizer and scheduler, concurrency managers that handles parallelization of a join, data partition managers, network communication code. So these frameworks are million lines of code, which is extremely complex. Then, now, let's think about the context for hardware heterogeneity. So what is a hardware heterogeneity? Right now, we're at a very exciting time where diverse spectrum of our hardware accelerators are being made on public cloud. Like Amazon F1 from AWS is a kind of example where it provides an environment for writing applications that could offload to hardware accelerator using FPGA. Intel has FPGA developer cloud, and also expensive hardware such as supercomputers and quantum computers are being made available as a public cloud services. And this is really extreme value position for developers and end users. You don't have to buy expensive hardware, you pay as you go. What is a developer workflow for high-level synthesis? Developer have an application, they profile for a while, identify that pink block of a code that is very compute intensive, and the process of writing high-level synthesis or offloading to FPGA is usually done through a process called high-level synthesis. You write that application so that it could directly map to the hardware circuit. It's usually done in RTL or a language called high-level synthesis. While you are doing this development, it's extremely long cycle because each compilation could be a couple minutes or 10 minutes. Hardware simulation could be orders of a minute or hour. And actual baking of hardware circuit takes even days or longer. So the development cycle is, could be long iteration or slow iteration. So you are probably hearing this heterogeneous application development where a portion could be offloaded to accelerator, many of you maybe for the first time. Why? According to US Bureau of Statistics, there's 1.8 software engineers available in US, while there are only 70,000 hardware engineers. This process of leveraging heterogeneity is inaccessible to most developers. Why? Because this rewriting or refactoring process requires deep hardware level, microprocessor level optimization knowledges that requires you to think about in terms of finite resources, data partitioning, parallelization, and pipelining. So what are the lessons that I learned by adapting tools into this data and compute-intensive domain? I have, for the past 9 years, I adapted and redesigned symbolic execution, FOSE testing, automated delta debugging, taint analysis, spectra-based photo localization. Many of these techniques that you are familiar in software engineering to this big data domain. And more recently, I adapted automated repair, automated refactoring, FOSE testing to incorporate hardware heterogeneity. This is a really important slide. What are the things I learned? There are many broken assumptions in software engineering community that doesn't really work in data and compute-intensive domain. Many fuzzing researchers thinks that the program runs fast to allow fuzzing, almost 1 million invocations per minute. It doesn't work this way. Program compilation also runs very slow in this hardware simulation domain, making techniques like automated repair very slow if you do not do specialization. We often think that there are huge repository of data that's available that we could learn insights of a domain-specific knowledge. If you want to be democratizing this technology that is currently inaccessible, we don't have millions of a GitHub repository to learn from and even build a large language model. And we cannot wait for those corpus to exist first. Oftentimes, we stay away big engineering challenges because it seems too hard. For example, symbolic execution doesn't scale, so I'm not going to try for Apache Spark. Injecting traceability takes up overhead, so maybe it's slow, and then we should not do this. But I want to emphasize that this is a lot of hard system engineering work, and it is interdisciplinary work. But all this, what we consider as an expensive analysis technique, is actually possible to do it with reasonable overhead if we think very hard about how to redesign these underlying systems and runtime. So with that, I want to thank my former PhD student, who's now professor of Virginia Tech, and also Qian. All right. Thank you.
So there are some very hard acts to follow in this world, and Miryung's one of them. Do my slides show up? Waiting for. Sorry? Technical people, do I have slides?
This one.
Ah, yes. Okay, so this talk is all wrong. I'm Tim Menzies from North Carolina State University, and I made the mistake of talking to someone smarter than me just now. And I realized what I wanted to, and having talked to Myra for 20 seconds, Myra Cohen, I realized what I want to talk about is ethics at the speed of AI. And so I hear a lot of people saying that they can't do ethics in a modern industrial setting, because in this modern industrial setting, one of the constants is the ship it mentality. And anything that slows you up, anything that stops you getting anything out the door, is just impractical to ask people to do that. And so I want to talk about what it would mean to do ethics at the speed of AI, where you're always making choices and always making ethical choices at every second, every day of what's going on. And I want to argue that you have many, many choices. I really do. I want to argue that something happens when I hit the buttons. Okay, so nothing's happening. And this is really good. Thanks very much. So this happened to me yesterday too when I was giving a talk, and I had to do the whole talk a cappella. We can try that again if you want, but if anyone can tell me, any technical person at the back can tell me why I've got no response to my email? Okay, let's try this a cappella, shall we? Have you ever considered the roles of hyperparameter optimization in modern software engineering? If I give you a large configuration space to explore, like the internals of a make file, you can have billions of options to explore. One of the unsung success stories of AI recently is AI tools for automatic configuration. And in those tools, we have tremendous success in very quickly working out really good ways to configure, say, MySQL to increase the return rate from queries, to decrease the energy. Configuration is one of the unsung success stories of AI in software engineering. Please consider what configuration means. It's a synonym for many other tasks. If we go to any sort of, this would really be great if the next slide came up of mine. If we go to fairness research, one of the things we find is that we have many choices now in our learners. And if we look at graphs of the accuracy of our learners And then we look at graphs of other measures coming out of our learners, such as the false alarm rate between men and women. We can find that the choices we make inside a learner can have dramatic impact upon the accuracy, as well as a dramatic impact upon the false alarm rate between men and women. And in these slides that I can't show you, I have all these examples where women are 5 times less likely to be able to open bank accounts, to get organ transplants, to get bail rather than going to jail, because of decisions made inside these systems. Now, with our AI tools, we can explore the configuration space. If you look at the search-based software engineering stuff that Myra works on, that I work on, we have a lot of examples where we can explore a very large space of options. Some of you may have heard of Software 2.0, where a development team divides into 2, and half that team knows how to care and feed an optimizer. And the other half does normal software engineering. We have a lot of experience in people doing optimization, and this is important to explore options. And this is how the talk was going to have started. I was going to point out, a lot of us are talking about the implications of large language models in our software. How many of us are talking about the implications of Starlink on software engineering? Elon Musk is putting up 24,000 satellites. The Chinese are not going to put up with that. They're not going to live under an Elon moon. They're putting up their own network of satellites. I can count 4 different initiatives putting up internet across the planet. In 10 years' time, when all of Africa is online and all of India is online, we'll have double, triple the number of programmers, at which point they'll be working for 1/20th of the current cost. Already, Bolivians are 1/5 the cost of running Americans. If we go all across Africa, we'll get a very different picture as well. I take it none of us in this room want to work for 1/20th of our current rate. Okay? I take it the people in this room want to be the people telling this army of programmers what to do. And these army of programmers will use all our large language models to do a lot of routine tasks. So I submit to you that a lot of computing is about to become done routinely by armies of programmers in Africa, South America, India. And if we want to have a job, we'll be the people telling them what to do. Now, if you look at the choice options, what usually happens in software is the amount of configuration options in the system increases polynomially, but our understanding of them only increases linearly. So there's this massive performance gap, this opportunity for automatic tools to explore all the options that we aren't exploring. Now, if you talk about the mathematics of that, here are these examples where you've got accuracy across here, and you've got the false alarm rate between men and women, and each one of these black dots is hyperparameter optimization. And you can see down here, here is maximum accuracy on, shall I give you a bank loan? But at this point here, women are 1/5 as likely to get a bank loan as men. And over here, organs. And over here is, shall I send you to jail rather than give you bail? So we're making choices inside our software, including how to click on these things, that have tremendous impact on how on the performance of these systems. We're doing them routinely as part of our current stuff. Now, if we talk about how to do that, I really like this sort of divide and conquer recursive random projections. This is exploration of PCA space. So find 2 random points and split the data on that. I like this sort of stuff. And what we notice here is there's a green region here we care about, a red region we want to explore. And if you actually start pruning this along the way, we don't have to look at both sides of this. We can just cover half of it. So I can explore n options in log n space. I can make choices about many things, like the energy consumption of the software, the speed of results in SQL, the accuracy and fairness of our systems. I'm routinely making choices in our software. And if we look at sort of, methods for making choices, like we want to, in requirements engineering, there's too many things to discuss. What do you discuss next? Test case minimization, what's the next thing to run next? Configuration, what to try next? How much of our time, day to day, as software engineers, is working out, of all the things you could do, what's the next best thing to do? What's the next best GitHub issue to resolve? Things like that. We're making choices all the time. And there's some beautiful mathematics of choices. Those of you who know TPE, a tree of Parsen estimators, know rigs like this where you've got tens of thousands of options to explore, and right now you've only done about 20 of them. And somehow you've decided you like these green ones and don't like those blue ones. And once you've got that going, you can say things, well, this is a region I like, this is a region I don't like. Build a very simple model, even a Bayes classifier for good and a bad and another for bad. And then this region here, if you know things like active learning or semi-supervised learning, finding any example that falls here where the probability of these two is about the same, this is the example that could most change our minds. This is the example that could most change the boundary between what we don't like and what we like. And so Google, when they did their Google Visor, used this sort of incremental exploration of let's find the thing in the middle there. And again, I can't use a clicker. And there's many other tasks that come down to, where do you find a mitigation? Where do you monitor? Where do you do safe operation? And if we go back, what's old is new. If we go back literally to Herbert Simon and the birth of AI, he talks about a science of design to derive courses of action amidst the changing situations into preferred ones. I submit to you that as a programmer, as a developer, every day you're making choices between options. And I submit that you should be thinking about those options. And there's a whole science of design here, which we do every day. Okay then, so got ethics. So I submit to you ethics. We want to do a lot of other things about ethics. We want to do everything. Didmar wants to tell us about diversity. You should talk to her about that. But also, day to day inside our projects, we make choices about systems. We make choices about systems all the time. So if you want to do ethics at the speed of AI, don't regard ethics as some external board thing, as a checklist to do outside. Write it into the choices that you make every day. You're doing test cases. Which test cases do you run next? Think about who's disempowered by your system, who's hurt by the software. If you're prioritizing what test cases to run, think about the answers to these questions and see what choices you get there. If you're doing requirements engineering and you're trying to explore, which options to explore next, ask yourself these questions and explore there. So I submit to you that you don't have to have a slower cycle to do ethics. I submit to you that some of the things we want to do ethically can be done at the speed of our current development processes. And then we do it using all these wonderful search-based software engineering methods that let us explore the space of options inside systems. And I hope I've given you an example of what a bad software is as used by an idiot. But here are all these tasks which are standard software tasks which amount to choices, which amount to things we would call in choice space. So, stop treating your software as deterministic things that do one thing. Treat them as a space of possibilities. Given that you're about to become the managers of a huge army of programmers working at 1/15 of the current cost, you will be directing their activity. So you'll be in charge of choice machines. You'll be in charge of choice machines. What choices will you make? You got the ethics to do them? Okay, thank you very much.
Thank you so much, team, and Miryung for the very nice presentations. Our next speaker is going to be on Zoom. I'm not sure how it's going to work. So the next speaker is Dr. Krysta Svore, who's talking about the path to quantum at scale. Okay, we can see you here.
All right. Hi, everyone. Can you see the slides full screen now?
Yes. Thank you.
Good. All right, thank you. Today I want to share with you the path to quantum at scale and the role of the cloud and really software engineering in that path. field, the truth that we've realized over the years, as we've really worked at understanding the power of quantum computing, is that the world needs quantum at scale. We need to reach 1 million physical qubits and beyond to solve and improve solutions to problems that are some of the most challenging for our world. The world really needs quantum at scale because we want to be able to bring a capability, a computational capability forward. We want to be able to take 250 years of, say, the next 250 years of chemistry and bundle it up into, say, the next 25 years, right, in order to help save our planet and feed our planet. Our goal with quantum computing, and in particular as we scale up, is to solve computational problems that are hard, right, that are challenging for our classical machinery, our classical compute machinery today. And this sits squarely in the space of quantum mechanics, in quantum in chemistry and material science. And while at first that may seem a bit niche, right, or specific, the reality is that 96% of the world's manufactured goods rely on some form of chemistry or material science. And all of those goods, 100%, all of those goods impact 100% of us, of humanity. Now, the world needs quantum at scale, but as it turns out, quantum at scale also needs the cloud, right? A quantum machine at this scale not only requires classical compute to keep it alive, but it also requires that to enable diverse access globally. A quantum computer is much like it's really an accelerator type of model. It's an accelerator to your classical compute. And so by necessity, right, quantum computing and classical computing will work hand in hand. And so it requires very careful integration of classical and quantum compute together to achieve the type of promise we see coming from quantum computing at scale. And while it's long been recognized in the field that indeed it will be hybrid, right? Quantum computing will come with a need, with an integration, with classical computing. Really the impact of co-designing HPC, AI, and quantum computing together in a cloud, right? As we're doing at Microsoft, we are working to integrate and co-design these three pillars of compute together and bring it to Azure, empower scientists, engineers, developers globally with this capability. While we realize that at the same time, we also recognize that by co-designing these three things and bringing them together, it really does bring forward three perhaps surprising capabilities for our future. And so I'd like to step through these three in the remaining minutes today with all of you. We start with unlocking a fault-tolerant quantum machine. What we mean here is really, it is with classical computing that we will unlock the ability to reach 1 million physical qubits, keep that system reliable, and enable it to run the types of computations we want to see run that bring us solutions that we cannot expect to get or achieve with classical machines alone. Now, the real key here is that while we have physical qubits today, we have quantum hardware in Azure today, right? These physical qubits are noisy. And to do the type of computation that will help us change the types of solutions we get, right? Enable us to have solutions around predictive computational design, around catalysis, solutions that could help us identify how to better produce a fertilizer, right? How to better capture or sequester carbon, right? These types of solutions require a large quantum machine, right? Upwards of 1 million physical qubits. And that means when we take these physical qubits that are quite noisy, we need to be able to protect them. We need to be able to correct the errors. And this requires pairing this with classical compute. It's really about taking a physical qubit, encoding it in many physical qubits, and a lot of additional classical computing, and enabling, right, longer and longer computational lifetimes of the quantum machine. We need to reach an error rate that's on the order of 10 to the minus 17 for these algorithms to be run reliably in a quantum machine, right? So we really have to be able to bootstrap from the physical qubit error rate to the logical qubit error rate. And this bootstrapping requires, first at the core a very good qubit, right? A qubit that's really just right. A qubit is analogous to a bit in classical computing. This is our notion of a quantum bit, a qubit. And this qubit, the physical instantiation of it, it needs to be small, right? We're going to ask to have 1 million of them in the system. It needs to be small enough, right? Ideally that it would sit on a single wafer. It also needs to be fast, because after all, we want the runtimes of the ultimate quantum algorithm to be less than a month, right? We want it to be practical. It should run within a matter of weeks or a month. And so the qubit itself, its operations needs to be fast. And we need to be able to control it. We have to be able to program the system. We have to measure out the outputs. We want to be able to do that reliably with low noise. So ideally you have a digital type of control. And so at Microsoft, we're working on a qubit that we believe is right in the sweet spot. It's right, just right among these characteristics, and it's called a topological qubit. Now, around the system, though, we do need that classical compute, and so we want to integrate right into Azure. And at Microsoft, we're working on integrating AI, HPC, and quantum computing together. To keep the quantum machine alive, we need some pretty amazing bandwidths. We need some pretty amazing amount of classical compute to keep the quantum machine alive. To give you a flavor there, we need roughly 10 to 100 terabits a second of bandwidth. We need a roughly, petaflop and upscale classical machine, closely architected, really custom architected with our quantum machine to keep the quantum machine alive, because we are taking 1 million plus qubit measurements every cycle, and then we have to be able to understand those measurements, correct the errors, and keep this cycle going. So there's pretty amazing classical compute capabilities here that we need to be able to address. Now that's kind of within the quantum machine itself, right, where we already have to have this tight quantum and classical integration. But at the same time, for these algorithms, right, when we think about computational chemistry, right, we want to understand catalysis, we want to simulate reaction rates, understand ground state energies, all of this to be able to better understand, say, a process like nitrogen fixation or carbon fixation. This requires also a large amount of classical compute in the algorithm itself. So we also need to pair this with HPC to do that classical compute, and we're looking at upwards of 1 million plus CPU, GPU hours that's partnered with runs on the quantum machine. So there's a lot of really interesting software engineering behind the scenes as we make this quantum machine scale. Now what's nice is out of this, already today we can start to solve quantum mechanical problems, right? As we work to integrate across AI, HPC, and quantum, we can already see promise and application of these solutions today. In particular with HPC automation, as we bring these chemical workloads, these chemical simulations of catalytic reactions, for example, to Azure, to HPC capabilities, we can improve the scale of solutions. So we can look at getting 1,000x in scale. For example, with ETH Zurich and Pacific Northwest National Labs, recently we published and produced a result, we call it AutoRxN. It's a service that enables speeding up these catalytic simulations by 10x, right, and improving the cost there. Now, as we pair that with the capabilities of AI, and then ultimately bring quantum computing where you will get higher and higher accuracy using the quantum machine, this will really transform how we think about running problems and finding solutions in computational chemistry and materials science. So the key is to integrate across, and together, as we perform that integration, there will be a really new set of opportunities for innovators, scientists, and developers around the world. It's this seamless integration across AI, HPC, and quantum that really will unlock new innovations, right? New innovations in particular, as I mentioned, in spaces like chemistry and materials science. Now, the good news is that you can imagine how those are going to come together, where you get higher throughput screening, higher accuracy by using all of these three together. But already today, you can get a head start. As we work on integrating HPC and quantum today, for example, you already can perform classical control flow on qubits, on quantum hardware in Azure Quantum today. And while these systems don't yet enable the types of solutions I've just discussed in chemistry, right, we still need to scale up to that 1 million physical qubits and beyond, it still gives us the ability to begin to program these machines, program the devices, understand the behavior, and develop new protocols that can really make the difference as we scale up. And so Azure Quantum is a public service today. You can jump in and use Azure Quantum to program quantum hardware in Azure. You can do everything from write code in whether it's Python or Q#, choose your favorite language. You can pair that with different available libraries and lots of samples that are available even in Jupyter notebooks. And then you can integrate with your classical software and simulate the behavior of that quantum algorithm or protocol. Further, you can actually estimate the resources at scale that would be required and see what size quantum machine would be needed. And then you can also, of course, run small instances of these algorithms on the quantum hardware that's available in Azure Quantum today. And so what this looks like in terms of the options, there's many languages, there's a large ecosystem around Azure Quantum in terms of enabling you to write quantum programs, test them out, simulate them, resource estimate them, and then run them on real hardware. We have a number of different quantum hardware backends, different quantum computers available in Azure, everything from IonQ, Quantinuum, Rigetti, QCI, and Pascal, in addition to many simulators as well. And so you can get started quantum programming, performing quantum software engineering already today. And as I mentioned, you also have the ability to take advantage of the chemical simulation capabilities as well that I mentioned, for example, Auto RxN that we've also released. And so the key is to get started today as we scale up. I encourage all of you to join us on the journey to quantum scale as we work to integrate across HPC, AI, and quantum computing.
Thank you so much, Krysta, for the nice talk. Now I would like to invite Myra Cohen to talk about the software revolution of obfuscation.
Okay, thank you. So I get to follow some really great talks. But I have to tell you, so I got asked to talk a little bit. I'm talking about something called the software revolution of obfuscation. And I got asked, what is the future of software engineering? And I started to run out of time. I had to come give this talk, and I panicked because I thought, I'm not really sure if I know. So, of course, what I did was I did what my students do. Please don't tweet this because this comes from ChatGPT, not me. So this was basically its answer of what AI was and of what the future of software engineering is. And I think it's actually pretty basic stuff. As a matter of fact, I looked at this and I thought, well, I can't talk about any of these things. And I noticed when Tom Zimmerman did something similar this week, he got a much better answer. So I think the problem is you have to ask the right question. So I went back to the drawing board and I thought, well, we're just not asking the right question. So I hope I don't get kicked off the stage, but I changed the question I'm going to answer. So what I really think I want to ask is, who are the future software engineers, not what is the future of software engineering? So I went back to ChatGPT again, and it basically told me that it can't provide information about the future, but that it could identify potential candidates. So I looked at what it said, and it said that they're going to have a strong foundation in programming, computer science concepts, etc. This is where I gave up because I realized I completely disagree with ChatGPT. So we're going to forget that, and I'll tell you what I think. So there's been, for many years, there was this group of people called, working on something called end-user software engineering, and they were looking at all the programmers that do things in business that look at spreadsheets and web applications, and all these people, their job is not really software engineering. And more recently, people working on Jupyter notebooks, and they've really been focusing on helping them make software correct, often without, just under the cover, without them really knowing what they're doing, just asking a couple of questions. And this is a really interesting area to look at, but let me tell you a little bit about the kind of people I've been working with. So I've been working with a lot of people in the sciences and biology and in other sciences, and this is actually a page called BioStars. This is their, it's their Stack Overflow version, so this is where they go to ask questions. This is about 5,000 responses to the word parameter. They have their own bioarchive where they're publishing. I just put in tools and I got, tens of thousands or hundreds of thousands of articles that are using tools. So they're all developing tools. In fact, if I go to climate science, I get many tools. We just heard about the fact that anybody can now build a quantum program, right? So this is actually an application. I work a lot, this is a predictive biology application. And you can see there are all these different apps that people can use. So there's hundreds of them, or actually thousands of them they can use. This is on a system called a predictive knowledge database, and they have tens of thousands of biologists using this. And this is kind of the environment. So they go in and they drag and they drop. They have workflows, they have data, they have apps, and they build different scenarios. So I can actually go in now and I can ask a biological question. It probably won't give me the right answer, but I can do that. Because I don't have the domain knowledge. I can't really understand the biology. So I can also do more than that. So anyone, it says here, can be a developer. So getting started is simple. You sign up, you get the code, you read the docs. Now they actually have some pretty good practices. You have to have unit tests, but anybody can contribute. It's all open source to this environment. Now, let's just move away from science for a second. I don't do a lot of machine learning, but I can go in here. I've done some really exciting machine learning inside of this rapid miner. Some of it's visual. It does auto-tuning. Although I want to caution that there are many other parameters in these ML applications that are not hyperparameters, and you don't get auto-tuning for those. So you really, but I can go in. Anybody can do it. As a matter of fact, my friend here can do it. And it's just a magic box. So I push a button and I get an answer that I've used machine learning for. So this is the problem. The problem is that we have simplicity. We like simplicity. It's important, but it leads to this idea of obfuscation. It creates these magic boxes. And it's sometimes very good. It's not always a bad thing. So we've moved our programming languages to higher levels, and at a low complexity, tasks can really benefit from this kind of hidden what's happening under the covers. But as we get larger space of choices, the need for our understanding increases. So I like to think about it. So this is a car. Anybody can probably get into this car. There's a very few things we have to push, dials. Once we learn how to use them, we don't think we can just drive. However, if I try to get into a cockpit, you notice there's 2 seats. There's tons of training, and the pilots that are driving these airplanes need to understand what all those buttons are doing. They train for hours and hours. They need to understand what happens when something goes wrong. They actually can't use this magic box. They need to understand what's happening. And I would argue this is what's happening in a lot of the software we're building today. So this is an article from Nature. This was an article, it was a big, people were really excited about this, except 3 months after it was published, they had to change the conclusion because of a software error. This is a recent article saying that we need more software testing in microbial bioinformatics. It's a call to action. And just to show you an example of what some of their software looks like, this is one of the most commonly used bioinformatics tools, the basic local alignment search algorithm, BLAST. This is just a parameter screen from the GUI version. Now there's also a command line which is larger. And so there's a pretty big set of choices you can make for the algorithms that are working underneath. There's a dynamic programming algorithm underneath that searches DNA sequences to try to find functionality. Why do we care? Well, people are using BLAST. So this is an example of somebody who's using BLAST to make some important decisions about COVID. So in about 2015, there was a whole bunch of blog posts about something going wrong with BLAST. So somebody noticed there's a parameter called max target sequence. This is the current documentation. So this was 2015. This comes from 2022. Number of aligned sequences to keep. That's what it says. So it sounds like it's a filter, and you just set this to some value, and you get back those numbers of sequences. So this continues. There's more and more stuff. This is actually an article that somebody wrote, because what they realized is that it's not actually a filter on the returned results. It's a filter in the first stage of the dynamic programming algorithm. So there's multiple stages. So by changing that parameter, it actually changes the results you get back, and it may give you more or less than what that number is you set. And this was somebody pointing out a paper that somebody had written who had explicitly set it to a value of 1 because they only wanted the best result. So they actually didn't search in the way they should have searched. And then, of course, there was a response from the authors of the tool, and I just wanted to point out what they said. The bug, first of all, they found 3 things. The bug was going to be fixed, but this is simply how BLAST works. So they weren't. This is how that algorithm works. You can see that they still have the same documentation. And then there was a shortcoming of the implementation of one part of it. I'm not sure why they don't call that a bug, but that's what they responded. So what I want to say is we have this sort of future of end-user software engineering. I call it end-user software engineering 2.0. And we have lots of different people. We have the people at the top are scientific software developers, may actually be more like software engineers, but I don't think you're going to find any of these people at ICSE, and this is one of the challenges. But they're actually pretty well trained. They understand software engineering. You also have people just developing workflows that other people are going to use. You have the data scientists that are also developing their own workflows. And then at the very bottom there, you have the scientists who just want to use these tools. They want to be able to trust them. They want to understand what they're doing. So moving forward, I think the future is, I don't have all the answers, but I think we need to think about ways to guide people and to do it in an unobtrusive way. They don't want to be developers. They don't want to learn about what's under the covers, but they need to know what's happening. So for instance, they might have something like this that just prompts them and says, well, you've changed a parameter. Perhaps you want to turn on some other mode and explore this a little bit more. We also need to provide ways to help them write specifications and list their assumptions, because their tools have many assumptions around them and they don't usually document those. The other thing that Miryung kind of talked about is this big data. A lot of them are using models and they're using data. So when something goes wrong and they get the result they don't expect, it's very hard to know, is it in the code or is it in the data? And so we need techniques there. And the last thing is that we need this idea of explainability and interpretability. So, we might use, people talk about using regression equations. I can't understand them. I don't think that some of these developers are going to understand, help me know what's happening by using that. We've used classification trees that might be a little bit better. It's visual. But I think there are hybrid recommender prediction systems. These need to be built into, I wrote Jupyter notebooks here, but this is the future, so I don't know what their environment will look like. It probably won't be notebooks at that time, but I think we need to build it into their environment, and we need to be talking to them. So my future of software engineering, as I said, is really who is the future of software engineering, and I think everybody's going to be doing this, making really a lot of decisions, building their own software. And as a community, I think we need to reach out and figure out what they're doing. So that's all I wanted to say.
So I have a question on the ethics side, probably also very related to Myra's talk on the obfuscation side of the talk. So ethics. I think a lot of the time, Tim, you might be talking about 2 types of choices. So I think the reason why I have an ethics board and all this checklist is the stakeholders feel the developers are making choices for them. When they make an implementation level choice, that choice have the implication to the stakeholders they haven't considered. So let me give you an example. For example, in US census data, you collect all this very sensitive private data. You want to release it. So you have stakeholders, a committee have to make a decision how much privacy to sacrifice to retain the utility of the data, because there's a trade-off choice to be made. The committee makes that. So that's not a choice for the privacy and utility of data. If you want to keep the data more private, you lose the data utility. The data becoming increasingly useless. But the utility is very important. You want to analyze this data to get benefits. So there's a choice the stakeholders have to make. They don't want the developers to make. So the developer basically makes a technology, expose those choices. There's a curve for them to select. Then after you select that curve, sacrifice this amount of privacy, then the system will implement that. Although in that case, you may argue, within that implementation, I got a lot of choices to make. That those choices doesn't impact the privacy and utility curve. However, what turns out to be is when you try to increase privacy, you also hurt fairness. This is like the developer didn't know, and maybe some of them didn't think we have time to ask the stakeholders. So they made some choices, the system being implemented, and you hurt people's fairness in terms of grants analysis and something. So I think my question is, how do you manage this kind of developer choices, whether intentionally or unintentionally, impacting stakeholder choices, which they don't think it's developers to make.
So you're talking about an initial set of choices which later on people discover, say, a privacy utility trade-off that means the initial choices have to be revised. So if right, I mean, you want...
It's like the developers making some choices in the implementation. That's a very severe consequence of choices that other people should have been made.
Right.
Like, it's not for developer to think, I want to sacrifice this amount of privacy.
So the core problem, what you're talking about, is that the oversight of the software occurred at the specification stage and stopped during the development stage. And so the thing would be to, how can we incrementally keep oversight going? The central problem, the thing I keep finding with all issues of ethics and all issues of discrimination is there's a situation where there's a small group of people making choices about something that affects a larger group of people. And the cycle I think we should be talking about is how does the larger group of people in a cost-effective way lean in and study what the smaller group is doing in a way that lets them change what the smaller group is doing. And I think there's mathematics there of the auditing process. And the good news is we have a lot of tools that can help that. If you consider what happens when the larger group leans in to look at law, we're talking about explanation tools, interpretation tools, multi-objective trade-off tools. We're getting pretty good at that. The other one is that the larger group reviewing what the smaller group does, I take it as their usual domain experts, they're not available all the time. They're busy people. So I'm imagining that this audit cycle happens infrequently, once a week, once a month, once a year. So what we want is something that gets generated from audit cycle 1, which is then available between audit cycles that can ring a bell if things are screwing up. And then when we get to audit 2, we want audit 2 to be somehow faster because we learned something in audit 1. All these things, explanations, rules, multi-directed optimization, these are things we have some handle on. So I think it's the smaller group, the larger group, how do they communicate and change each other's minds?
Yeah, thanks. Can I just quick question? Do you think the smaller group is the developers, the larger group is the stakeholders, the community, or you think that may misunderstood you mean the smaller group are developers, the larger group are technical auditors? But then where is the community and the stakeholders?
Well, let's look at two on definitions. The large group are the people affected by what the smaller group does. They could have been the initial stakeholders. They could have been the broader community that this thing gets delivered to, So yeah, but I think, but what's exciting about this, call it the penny farthing model, small wheel, big wheel. What's exciting about the penny farthing model is we can lean in and we can talk current technologies that give us much help on many parts of this penny farthing model.
Hi. Just have two quick questions. First one for Tim. You said at the end that I submit to you that if you, that's your very typical submit to you. So that if you do ethics, it's not going to take you longer than if you don't do ethics. I think that was the gist of what I heard anyway. So I'm just wondering whether you have any evidence to show that, because I know that when we talk to people, in companies who are at the beginning of the journey of perhaps doing AI ethics, they are always concerned about the additional time needed for auditing, for monitoring, for everything that they need to do to make sure that what they're doing is ethical. But you're saying that it's not going to take you long. So I want to know if you have evidence.
We already know in software 2.0 applications that there are teams who are doing the care and feeding of the optimizers. So in a commercial framework, they've found it cost effective to have one team doing the standards, UI, modeling, database development, packaging, and there's another team in a cost-effective way are doing the optimization work. I know that a certain company on campus where I work, who do a lot of commercial text mining, do a lot of optimization work as part of their normal cycles. Okay, so the thing is to But I wouldn't have thought that was your question.
I'm after evidence.
I would have thought
Evidence.
you'd be ruder and say, surely ethics is a question of social context, and that requires elaborate, extensive manual discussions between stakeholders to come up to some shared opinion. Let's do all that, and there are other people doing that better than me. There's something I know how to do, which is to configure something quick. And I'll say for the bit that I know what to do, I think we can speed that stuff up. Okay, so there's two parts, and so let's not pretend I've got solutions to the whole world, but let's say that there's at least the exploration of options at runtime, the ongoing auditing process. I think that we could speed up.
Yeah, actually, I want to kind of chime in and discuss a little bit about privacy as well as ethics and its relation to this data-intensive software development. So one, I think this issue of privacy-related ethics is actually necessitator or motivator for doing more research on debugging. So right now I'm collaborating with Amazon Web Services, and debugging is harder because the developer cannot see the input triggering failure because it could have a customer-sensitive information, right? So in some sense, I think all this work that we've been doing in terms of debugging is becoming even more necessary when you cannot really identify or you have an input but do not allow developer to see directly, right? Another thing that I want to mention is that, as I was doing more research on this big data analytics field, compared to like regular software system, finding benchmark is much harder, partially because of the data and code is a very interconnected thing, right? Like, so code doesn't run unless you have an input, but input often has privacy-sensitive information, so companies are less reluctant to release it together with the code, or even like do not release anything, both code and data, right? Like, so, yeah, I just want to make that connection that this issue of more data, right, or big data-intensive development, there's a huge motivator that's a kind of privacy-related or ethics-related motivator for doing more research in this area.
Well, so I'll just add that, Tim's talking about optimization, and this is exactly what I'm worried about, is because you're doing automated optimization, and you may be making all the right decisions, but somebody still has to decide which parameters to optimize, and if that's being done automatically, unless we can provide some of that information back, and those are those breadcrumbs, we may be missing certain aspects of fairness we're not thinking about today, or certain aspects. So I think a lot of it comes down to we still need to open up some of those boxes, which then have security issues. But I feel like we really still need to be informing people of what those things are that we're tuning, not just doing it automatically.
So the penny farthing model, there's a small group of people doing things which affects a larger group, and we want a cycle of information and improvement between the two of them. And in this area, we're in violent agreement. Also, we need to distinguish between optimization of the symbols currently inside the box and also the exploration of the symbols not inside the box. It's very exciting to look at some of the requirements engineering methods. The repertory grids of George Kelly as a way to explore the symbolic structures of the conceptual structures that people aren't saying right now. So we need methods to do better with the symbols we know about, and we need methods to find the concepts we're missing. So inside the box and outside the box.
Krysta, do you want to add something? Sorry for... Can you hear us? No, you can't hear us. So maybe we go to the next question and see if we can solve it.
I have actually a question for Krysta. Do you hear me? You do? Yes. Sorry, I'm Patricia Lago from Vrije Universiteit Amsterdam in the Netherlands. You gave a great overview of the technical promises and of quantum computing and figures about the technical aspects. I was wondering if you can also give some figures about the energy consumption of quantum systems and the energy needs that they have. And maybe in trade-off, if you have them, so the trade-off between the technical promise and the energy needs.
Yeah. In terms of the energy consumption, right? The quantum machine itself is running in a dilution refrigerator, and so as we scale up to more and more qubits, we're really still running that same system, whether it's 1 qubit or a million qubits, all running within the dilution refrigerator, right? So in terms of that energy consumption, the consumption actually comes from running, more of the energy is actually coming from the classical compute, right? So we're running, custom architecting, as I mentioned, essentially a petascale machine to help keep that quantum machine alive. But the fridge itself is not that much power consumption, energy consumption. So it's really looking at the classical compute, and the considerations here as well is that we need to have that classical compute in the case of keeping the machine alive very, very close to the quantum compute itself, close to the quantum chip. So we've actually looked at and invented, we have papers on this on the archive, cryogenic CMOS, for example, right? So custom circuitry that we can use to help control our quantum system, and it sits, our qubits are at millikelvin temperature, so almost absolute zero within this cryostat, and then our CMOS is at higher, slightly higher temperatures, but we actually, work to engineer this, keep the thermal load down. And so really the power consumption is more on the classical processing than the quantum machine itself.
Any figures? Because I know that cooling is quite demanding. For quantum, yes. What you're saying to keep the temperature, the low temperature that is necessary.
Yeah, no, it's not. I mean, it's not that demanding. Okay. Nothing compared to running, a data center workload, right? It's much less. I can get you.
Yeah, I have a question for Miryung. So you mentioned big data, Spark, and all these systems. And if my understanding is correct, your how can I say interest was mainly at application level. But you should also consider the infrastructure, I think, because in these days, it's just infrastructure as code. So you manage it by means of other software. So can you comment a bit on the interplay between the two aspects? Thank you.
Thank you, Luciano, for this question. So in terms of test input generation and debugging, we focus on application bug, but this is not just looking at the underlying infrastructure as a black box. To enable that debugging or traceability, we actually had to re-engineer Apache Spark runtime. And that's actually one of the things that I wanted to emphasize in this discussion, that, I think if you look at a lot of proceedings in ICSE and FSE, ASE, most of it targets Python, Java, C++. We work right above just a compiler, right? Or in that level, right? We don't really think about these underlying layers and runtimes. And we think of this as hairy, time-consuming, labor-intensive, system engineering work. And then what I learned through this experience is that we need to really appreciate these level of work, because we cannot design interactive debugging, automated debugging, all these things without actually, instrumenting the runtime. Because if you do it really naively outside of this runtimes and box, then you are incurring huge overhead, right? You have to store a lot of information. Replay debugging is hard. So some of the work that we've been doing is actually rewriting runtime to figure out what is the right point of a snapshotting for replay debugging. How do we add traceability through data provenance, right? So that we could tag each data. And again, program analysis, people think, oh, we've been doing taint analysis, static information analysis for a long time. What's new here, right? But really, I think the nugget is engineering, how to do it at the scale of terabytes of data, right? In the distributed computing systems where information is stored on multiple nodes, right? So.
Yeah, just, a bit of personal, background. So years ago, we did a bit of work on Spark, and we submitted it, we asked TSE. And, the first reviewer said that it's not software engineering, it's system engineering. So, we had to select another journal. But anyway, in the end, we made it. Can I ask a second question?
I want to jump in and make a point right on the definition of software engineering. The more we do software engineering, the more we touch the world. Everything is software.
That was exactly my point. But
astronomers have to learn how to, grind the lens, and then they use the lens to look at the world. So I often get this problem when I submit to say TSE, where they say you're not talking about coal-face programming, therefore you're not software engineering. When I think about the space of what software touches, the infrastructure needed, it's vast. And one of my favorite papers is an FSE 2022 paper where they talk about requirements engineering for sewage management. and it's in FSE 2022. And that makes me so happy.
Smart reviewers.
Sorry?
Smart reviewers.
Smart reviewers. Software is everywhere.
Can I ask a second question to Myra? Control engineers have been dealing with obfuscation for decades. They've been using MATLAB, Simulink, and this kind of things, to create, I would say, great control systems. Are we supposed to do the same? And we are just, a step behind?
Well, yeah, I think that, it depends on the environment. As I said, I think in smaller systems, I think it's okay, but we're providing systems that, have these huge configuration spaces and, in the order of, 2 to the 50. And people have to be able to navigate those spaces. And when you get into those spaces and that starts impacting what you're doing, or you have models. So I'm currently looking at some systems where we've tried to compare 4 different systems that do the same thing, that were written by, different groups of people. And none of them give us the same answer on fundamental questions like how many of X is in this model. And yet they're all coming from the same model. And so I think, some of this is everybody's building these in a distributed way, and we're giving them that high level so they can quickly build it. But then what's happening underneath is not being exposed at all, and people that are using it are getting answers that they don't understand. So I think control engineering, and simulating, it's probably, it works for certain environments, but I think that at some point, even in a MATLAB environment, I would argue I'd want to still have some information about what's going on under the code. Yeah, so we're using MATLAB for some stuff we're doing, and we still look at the logs, we still try to read those, we still try to understand what's happening. So we don't need to do it while we're actually programming, but when somebody's using it, they should be getting some information. That's why I'm calling it breadcrumbs. I think just something to just warn somebody that these are some of the assumptions that have been made. And I don't know how to do that yet, but we're trying to think about it, right? Does that answer your question?
Yeah. There's a comment I want to make here about some commonalities. Miryung's talking about uncertainty in test cases and how you can't just assume deterministic world, you've got to explore. Myra's talking about how you can't just give people single dumb answers, you have to give them breadcrumbs and ideas. And I'm talking about some penny farthing model where there's a continuous feedback cycle between developers and the developed. And so what I'm hearing here is a new definition of software engineering, not as the delivery of a deterministic piece of software, but as a science, as a exploration of walking the world and seeing what's going on. And so we turn ourselves from, Dijkstra proving theorems into Sherlock Holmes with a microscope looking around seeing what the hell's going on. So software engineer is detective, not as incremental refinement of specification.
Okay. I have a question for Professor Miryung. I know you are experts in heterogeneous systems. So in your opinion, what would be the biggest challenge for applying the existing software engineering techniques to the heterogeneous systems?
So I think one is about the programming or rewriting, because as I said, the people who could right now write these custom accelerators that maps to kernel computation needs a microprocessor level knowledge. So even though the languages and new DSLs are available, specifying like how to partition data or how to parallelize, I think many of computer science 101 students who know how to program in Python cannot do that, right? So I think there is a significant learning curve. I think another challenge probably may be related to Castilla too is that, in addition to FPGA-based accelerator, we also looked into quantum computing framework or differential testing for quantum computers. One of the challenges in this domain is that, it's not like accelerator is magic. It actually is, for specific algorithms or a specific domain. So even trying to figure out like how to rewrite or what parts are rewritable under what architecture or under what kernel computation, I think that requires significant knowledge, right? And I think, we as a software engineering people think, oh, this is a computer architecture problem. It's a problem for people who go to ISCA or, Design Automation Conference or ICSE. But I really think in the future, that is our problem, because already architects and computer architects are all kind of moving into space that we're becoming a compiler writers, right? There is an innovation in hardware, but to leverage that innovation, we need a better mapping from high-level software to these low-level circuits. Yeah. Maybe Castilla can answer some.
Yeah, maybe just building on that a little bit on the quantum side, we've done quite a bit of work on making it really simple, on finding higher level abstractions that make it easier and easier for software engineers to, jump in and write quantum programs, right? You really have to, you don't want to have to think, right, at the level of the architecture. You don't want to have to think at the level of error correction and the intrinsic operations. We really want to elevate that and make it easy. And then on top of that, to the point of the accelerator model, right? It's a very, very hybrid model here. And so you're looking at, how do I separate this computation and put what's really required to go on the quantum machine, and what's really required to go on the classical machine, push as much to the classical machine as you can, right, to the classical capabilities. So you have to really carefully separate out, what you do where. And ideally, that becomes more and more automated in our future, right, with other tools and capabilities that help decide what computation, what aspects, which subroutines should go on which part of this very heterogeneous compute fabric that I have access to, right? It's really not the case that any individual really knows the best of all of the capabilities that are sitting at your fingertips in the cloud, right? So we actually also need to develop capabilities to enable that more automatic automatic separation of what should be computed where and how. So it's definitely something we think about when we think about building out the quantum stack, and the need that it needs to be so tightly integrated with all the other capabilities in the cloud. That's something that in that programming framework you really want to be able to capture as well. And it's, as is pointed out, it's not easy to identify what is best to run on the quantum machine. I did want to just make one more mention. I think on that power consumption piece, I was just making the point, right? It's the classical compute that's really expensive, but maybe you're looking for a number. I mean, a dilution refrigerator requires on the order of kilowatts of power, right?
Okay. Yeah, all nice discussions and new insights, but. So software is eating the world, we keep saying that, and I am also a software engineer, we are all software engineers, but outside of our domain, that's not always the perception. So, and we have to deal with software-intensive systems. We have to deal with different domains in which people apply different disciplines. Then we have to face the interdisciplinary research. What we then observe is like the interdisciplinary research or methods, they are actually missing, right? So now we have sometimes the belief, well, we should just do software engineering and just apply our approach. And maybe do research software engineering, that's already one step further. But beyond that, how do you see interdisciplinary research in which software engineering is just one of the disciplines and maybe not the dominant discipline? Or maybe it should be the dominant discipline, I don't know. But often we have to cope and we have to develop not just software, but software in different disciplines, right? I'm from a Wageningen University, it's a life science domain, so, and we did many projects with other domains. We just see these methods, software engineering methods, simply don't always align, don't always scale. So even our tools or abstractions. What's your opinion about this issue?
I can start on that one. So I've been working a lot with people, as I said, in bioinformatics, and it takes some time because we speak very different languages and we have very different approaches. For instance, I've watched people try to take somebody else's software they've built and run it, and they're not happy with the results, and then they just throw it away and rebuild it and write their own because they assume they can write it more correctly because they don't have that software engineering background, rather than trying to debug and find out what's happening. So I think you have to find collaborations, and you have to sort of come to their table. I spend a lot of time listening to conversations I don't understand about biology, but then I try to slowly interject some of our ideas and try to work on these tiny little bits that maybe can work together. But it's hard, and it's hard to publish in a place like ICSE. It's hard. We're trying to go out to their community, but obviously we have the same issue there because I think most research communities are really set up for a specific community. So I think it's challenging, but I think we have to make the effort. And I think we need to learn. That's why I talked about who are the future software engineers. I think we need to learn what people are doing and how they're working. They don't work in the way that we normally work. They don't approach software. They don't debug the way we debug. And you can't just look at them and try to superimpose our ideas on them. We really need to try to figure out how they're doing it and then slowly provide them with evidence that that you can help them. And then you have to also let them lead on some of their topics. So that's all. I mean, I don't think it's easy. So.
I absolutely agree with Myra. I was actually thinking about yesterday's Gail's talk and, how we should really immerse ourselves and do more, observing how developers work. I think as computer science and software engineering is expanding in this data and compute intensive domain, I think we need to now observe how climate scientists work with the software systems. How DOE engineers work on while they're building some sort of physics simulator, how they work with software system or how they maintain. Because I think to me it's really important, but our community somehow thinks that these are niche population, right? That's not the mainstream developer, right? Because we often think of software engineers sitting on Microsoft, Google, Amazon or Facebook writing, software system, right? But we don't really think of as these data scientists or data engineers or just the scientists. Yes.
So I'm funded by NSF to try and apply empirical software engineering stuff to computational science, to anyone doing material science, and we've recently got data on 161 software projects where we interviewed the computational scientist, massive mail out sort of thing, and said, what are the things you think makes a project successful? And so we started with the SE theories on what makes something successful. And that was and call those H1 through H7. And then we did the interviews and we got H8 through H12. And then we started building predictors. And the predictors start with H0 through H7, and then we add in H8, H9, H10, H11, trying to see what value added were the hypotheses from the computational scientists. And right now, with the microphone turned off and the door shut, H8 plus added nothing. So they talked about scientific rigor, and which we could measure by some surveys, and they talked about this and that. And what we're back to is that the H0 through H7 from SE were the main predictors for future health of the projects, which I haven't quite told the computational scientists yet, because I had to do that very carefully. But what it does mean, maybe, is that there are some beautiful uniform principles in software engineering. Like, who remembers the foundation and the principle of psychohistory was that people in groups have predictable properties. Maybe they do. I can't be sure about this now, but we're writing this up over summer. But there might be some beautiful general principles from SE that hold across lots of domains, which get back to me on. Give me a ping in a month, and I'll see if I can. I'll send you a preprint.
Yeah, thank you. So,
if I can maybe add a comment as well on that, with regard to really observing and watching the different types of software that's happening, right? You mentioned DOE, for example. I think about supercomputing, right? The types of workloads you run on a supercomputer. That's essentially when I think about what Azure is, right? We're running those workloads now in Azure, right? And so you're engineering these workloads. What do we do for our program? I spoke more about the software to program the quantum machine, to keep the machine alive. But at the same time, how do we go develop that machine? We're doing extensive physics simulations, very, very expensive simulations in Azure of device physics, right? Modeling that physics, doing extensive simulation of materials, material stacks. And so there's a ton of software engineering that goes in to actually, build out models of the device physics of the materials, and then work to validate that when you actually run it on the device itself, which also requires yet another software engineering stack to have experimental level capabilities on new devices, right? Devices that have very different properties than what we have classically. We need to extract that data, analyze that data, compare it to these models, right? And iterate extensively. And the way we make rapid progress there is having a really great loop, right? And a lot of extensive software engineering in that loop to validate, debug, move quickly, have agile development, right? And iterate. So it's, I think there's a real opportunity in looking at that. And at the same time, a lot of these workloads weren't previously run in the cloud, right? So then there's also how do we engineer and bring these workloads, very different, more computational science type workloads to the cloud, right? It's a huge opportunity. It's things that used to be done very much on-premises clusters, right, that were, that you would kind of manage and operate. But now there's an opportunity, right? As I mentioned, we brought some of these workloads with AutoRxN to the cloud, and we're continuing to do that. But we really need to bring those workloads to the cloud. Think about the software engineering we're bringing forward there, and what's different. I think there's a huge opportunity in looking at the different disciplines and how those disciplines do software engineering, and then how we can do it better together.
Okay, thank you. So we only have 4 minutes and 2 people who've raised their hands already. So I'm just going to take their questions, and the discussion can continue over lunch after that.
Okay, thanks. So I have a question about today we're talking about a lot of different domain related, from the big data to AI and to quantum computing. But it seems if we can look at each of these domains as a box, so for the software engineering research, so it seems we have to understand each of these boxes. So whether in the future of the software engineering, whether the researcher in software engineering should be Superman or Superwoman to know each of these domains, or in software engineering that we can find some like grand the granular information theories. So what's your opinion about the future of this research?
So I'll just be quick because I know we're running out of time. I actually think that as software engineers, we don't have to do it. I think the problem is that everybody else is going to be a software engineer, and what we need to be able to do is help them become software engineers without the title, because all of the scientists, that domain knowledge is really important. So they're going to be building the software. We're going to be building techniques that help them build the software using principled software engineering processes, but not necessarily letting them know that. So we have to guide them somehow. So that's what I think. That's my future.
I think of this like all these domain scientists or different groups of people, like sort of expansion of a computer scientist and expansion of a software engineering. And I think the key challenge that we have to address as a community is like, what are the underlying principles that transcends across the different domain, and then how we enlarge those principles. And what are the just wonderful heuristics in each domain that may not translate. So I'm actually really interested to hear Tim's perspective, because he said some of these underlying principles from software engineering is a key predictor, while the domain-specific one is less.
Well, if we double-click on that, everything goes back to Herbert Simon, the design of the artificial. Like I'd rename software engineering AI and say it's all about how humans explore the world. And I think there's general principles about that. But just specific to your point about having to learn too much. Okay? Now, as a software engineer, I know less about LL1 parsing than I do about multi-vector optimization. Even within what we might call software engineering, I've made my choices as to where I put my focus. I think SE will be an evolving, massively changing system, and I think we should tell us and our students that they are on a boat where the currents are going in different directions, and there is so much exciting to think about in this world, and we want to help people think broader, not narrower, about these problems.
So if you can hear me, Krysta, do you want to add something?
Yeah, I mean, absolutely. It's definitely the case. We shouldn't all have to learn everything, right? I think the key is finding the right ways to bring the best of the scientists together, with that, we need the domain knowledge, and we also need people, software engineers, that are thinking about how to really develop the best platforms, the best interfaces, right? We have to think across, right? I think we do really want to bring many different techniques together, many different areas together. The world, the cloud is very, very heterogeneous, right? In all the different compute capabilities you have there, the different services. So I think in software engineering, we can't expect to know it all. And so it's really finding the right frameworks and abstractions. And, at the core, we need to be able to communicate with everyone around us.
Okay, thanks.
And the last question is our panelist.
Yeah, hello. So I'll try to be brief. I know I'm aware of time. Thank you all for those presentations. Some of the bits and pieces of what I'm going to ask have been touched, but as we introduce new automation, new AI techniques, and our future software engineers have to collaborate with this AI, we risk as well the possibility of dependency on those tools, and yeah, just taking for granted that whatever the tool replies is the answer that we should be taking. We've seen examples with that with ChatGPT recently, and we have to train these software engineers to see options and explore. My question is, what are the challenges that you see, and how do we address them when we're training these future software engineers, the next generation of software engineers? What do you see there? If you want to comment or expand there.
The challenge I'm seeing in training the next generation of software engineers is that they're not seeing choice. If I literally give my grad students, not the PhD level, but the masters, and say, here's design 1, give me design 2. Right? Show me another way of doing it. You've gone to the manuals and found this mashup of the system, or you're maintaining this system. Give me an alternate design. So we're not teaching, or they're not hearing anymore about architectural choice and design trade-offs. So the reason I explore choice is that I think it's a core problem. Just the idea that there's more than one choice.
So I come from a testing background, so I would say we need them to be well-trained in testing, because testing is just exploration, it's sampling, and if we really make sure they understand those concepts, then they'll start to see that perhaps there are other options or other ways to use systems. And so I think we really need to focus on ensuring that that's being taught and that we can train them on that.
So my 2 cents on this is that I think we as a software engineering community emphasize a lot on abstraction, and I think which is powerful, but I also think we need to train our students to look at what is underlying systems or underlying layers of a complexity, right? Because, there are machine learning developers who only know how to work at the level of a PyTorch, but there are also people who understand what are the underlying runtimes or what are the compute environment that they are running, right? So I think it's a balance, right? Like how to leverage abstraction, but how to be able to also see the complexity underneath. Yeah.
Krysta, do you want to add?
Well, when I heard the question, my thoughts jumped to code review, right? Code review is such an important step in what we do in my team at Microsoft, right? We do a lot of code review. And so when you think about choice, right, you're also invoking choice in that review process and giving guidance and helping people learn together. I think when we think about the power of the AI models and pointers coming from that, right, I jumped to code review. It's much like learning how to do a good code review or taking the feedback from a code review, right? You still have choice, right, in what you're going to check in and decide to do, and that's a real skill to be able to make that choice among options. Think about maybe it's a higher level of abstraction, maybe it's a better interface, maybe it's whatever it might be, understand the complexities, as just was said, right? Maybe there's a better way to bring those complexities to life or to remove some of them. But it's all, to me, it's a bit like a code review, right? You want to be carefully reviewing, profiling, understanding the code, and then making suggestions and changes accordingly, whether that's coming from a human or AI.
Okay, thank you so much. Thanks a lot to our speakers and panelists for the time talking to us, and everyone for attending this session and also the interesting questions.